Good morning, students. In this session, I am going to complete that chapter, Work, Energy, Power. I am going to complete the chapter, Work, Energy, Power. Work is nothing but the product of the force and time of action. Force and displacement. Work is that product of the force and displacement. Work is a scalar quantity. Whenever we take that a body is there on a horizontal surface, let us suppose this is the horizontal surface. On this horizontal surface, a block of mass m is there. A block of mass m is there on the horizontal surface. If we pull it by a force, this is the force that is acting to pull it. F bar is the force acting to pull it. As a result, the block, if it moves on the horizontal surface, on applying force F, if the block that moves along the horizontal surface like this, then the angle between the force and the displacement is taken as theta. Displacement is F S bar. Then we'll take that work done W is equal to F bar dot S bar. F bar dot S bar is the work done. This work done W is equal to Fs cos theta. Fs cos theta we may write based on the angle, maybe positive work, negative work, or zero work. First one, if I take that angle between the force and displacement is 0 degrees. If the angle between force and displacement is 0 degrees, then work done is equal to Fs cos 0. Means work done is equal to positive work done. This work done is equal plus Fs will get it because cos 0 will be equal to 1. Work done W is equal to F into S. This is called as the positive work done. Next, whenever we take angle between the force and displacement is 90 degrees, means if they are right angles to one another, then work done W is equal to Fs cos 90. Cos 90 becomes 0. That's why work done is 0. Next, if theta is equal to 180 degrees, that means let us suppose a bucket which is filled with water. We are pulling up. Displacement is an upward direction. In such case, force is due to the gravitational force. The weight is due to the gravitational force. Then angle between that force F is equal to mg and F is equal to upward direction. Angle between the force and displacement is 180 degrees. In such case, work done W is equal to Fs cos 180. Cos 180 minus 1. Therefore, work done W is equal to minus F into S. This work done is called as the negative work done. Right? So, angle between the force and displacement is 0 degrees. Work done is positive. If the angle is 90 degrees, work done will be 0. If the angle between the force and displacement is 180 degrees, the work done is called as the negative work done. The unit, SI unit of the work done is SI unit of the work done is joules. So work done W is equal to Fs cos theta. If they didn't speak about any angle, we have to write that work done W is equal to F into S only we have to write. If they didn't give what is the angle between the force and displacement, then W is equal to F into S only we have to take. So W is equal to F into S. Its unit is taken as joule. SI unit. Our CGS unit is erg. Dimensional formula when we write, dimensional formula for that M1 L2 T power minus 2. M1 L2 T power minus 2. This is that dimensional formula for the work done. This work done may be due to the variable force. We'll say that work done by the variable force. Work done by the variable force. W is equal to integral S1 to S2 integral S1 to S2 F into ds. This is the work done by the variable force. This is the work done by the variable force. So then work done in expanding the gas. Let us suppose work is done in expanding the gas at constant pressure. We are expanding the gas, nothing but we are increasing the volume of the gas. Work done in expanding the gas. Work done in expanding the gas from the volume V1 to V2. Work done is equal to PdV. dV for change in volume. Then work done is equal to integral V1 to V2 PdV. This is a dW is equal to PdV. So W is equal to integral V1 to V2 PdV we will write. So then let us suppose work done in lifting a mass through a height h if you want. Let us suppose this is a block of mass m is there that we have to lift to a height h. We have to lift it to a height h. Then work done is a block of mass m is there. We have to lift it to a height h. Then the work done is W is equal to mgh plus 1 plus h divided by r. 1 plus h divided by r. And if height is much less than that of the radius of the earth, in such case we will take work done is equal to mgh. Work done in lifting a block of mass m to a height h is mgh. Let us suppose a work done in compressing or elongating the spring if you want. Work done in compressing or elongating a spring. Work done W is equal to half F into X. Work done is equal to half F into X. F for force, and x is the compression or elongation. R half kx square. K is the spring constant. R will take half f square divided by k. These are the formulas in compressing or elongating the spring. Let us suppose a spring of the spring constant k is there. If the spring of the spring constant k is there, let us suppose it is a spring of the spring constant k. If we extend this spring, if we extend the spring through a displacement x, if we extend the spring through a displacement x, the work done W is equal to half kx. F is the applied force, k is the spring constant, x is the displacement, x is the displacement, F is the applied force, k is the spring constant. So half fx or half kx square, half f square divided by k. These are the formulas in compressing or elongating a spring of force constant k. Let us suppose a rod of length L is there on the horizontal surface. It is a rod. Let us suppose a rod of length L is there. A rod of length L is there on the horizontal surface. A rod of length L is there on the horizontal surface. Then work done in lifting it in the vertical position. It is that length of the rod is taken as L. We have to lift it to the vertical position. From the horizontal position to vertical position, we have to raise. This should be raised like this. Whenever we lift it to the vertical position, up to its center of mass, if you lift, that is sufficient. Length is taken as up to center of mass. If you lift the center of mass, body automatically will be lifted. That's why work done in lifting this mass, a rod of length L, from the horizontal position to vertical position, mgl divided by 2. Work done in lifting a rod of length L from the horizontal position to vertical position is mgl divided by 2. Work done in lifting a rod of length L from the horizontal position to vertical position is mgl divided by 2. Now we have discussed, earlier we have discussed that work done in compressing or elongating the spring. So if you want to extend the spring, let us suppose initial extension is taken as x1, that we want to increase its, we have to increase to that elongation x2, then the work done is to be calculated. Work done in increasing that extension of the spring from x1 to x2 is half k into x2 square minus x1 square, half k into x2 square minus x1 square. This is the work done in extending the spring from the initial displacement x1 to x2. Okay, next, whenever we take a simple pendulum, it is a simple pendulum. A simple pendulum of length L is there. Then the work done in rotating it through an angle theta, whenever we want to raise it from the lower position to certain height, some work is needed. That work done in lifting from the mean position to certain extreme position, work done will be equal to mgl into 1 minus cos theta will write. Work done in displacing a simple pendulum from the mean position to through an angle theta, the work done is mgl into 1 minus cos theta. mgl into 1 minus cos theta. This is for the simple pendulum. And for the rod of length, this is the pendulum. It's for the pendulum. For a rod of length L, Let us suppose it is that rod that is suspended in the vertical position. A rod of length L is suspended. A rod of length L is suspended in the vertical position. Then the work done in lifting it, then the work done in rotating it through an angle. This is the rod. Earlier one is the simple pendulum. Let us suppose a rod of length L is there. That should be lifted from the vertical position to through an angle theta. Then the work done is mgl by 2 into 1 minus cos theta. For the simple pendulum, if you pull the simple pendulum from the mean position to extreme position, work done is mgl into 1 minus cos theta. Here L by 2 won't be there. But if it is rod, a rod of length L is rotated through an angle theta from the mean position, work done W is equal to mgl by 2 into 1 minus cos theta. W is equal to mgl by 2 into 1 minus cos theta. This is the work done in lifting a rod of length L from the vertical position to through an angle theta. Through an angle theta. Let us suppose a ladder is there on the horizontal surface. A ladder of mass M is there. It is a ladder. L-A-D-D-R. Ladder. A ladder of L-A-D-D-R. A ladder of mass M is on the horizontal floor. It lies on the horizontal floor. Then when we want to lift it to the vertical position and held it to a wall at an angle theta, we have to keep this to a wall. We have to keep it to a wall. At an angle theta. We have to keep it for a wall at an angle theta. We have to keep it for a wall at an angle theta. We have to keep it to the wall at an angle theta. Then up to its half of its length, it is sufficient. Length of the ladder is taken as L. Up to L by 2, we have to lift it. Then work done in keeping this ladder or work done to hold this ladder to a vertical wall at an angle theta is mgl by 2 into sin theta. Mgl by 2 into sin theta. This is the work done in keeping this ladder to the vertical wall. Let us suppose a bucket of water which is filled with liquid. We have to lift it through a height h with the help of the rope. A bucket which is full of water with the total mass capital M is there in the water. Let us suppose this is the water. In the water, a bucket of mass, total mass capital M is there. In the water, a bucket of total mass capital M is there. In that, a bucket of total mass capital M is there. Then we have to lift it. Then we have to lift it through by using a rope of full length. We have to lift it. We have to lift it through with the help of the rope of length L. Then work done in lifting this. Let us suppose M is the mass of the total bucket along with the water, and mass of this rope is taken as a small m. Then work done in lifting a bucket of total mass capital M from water to that entire length of this rope. That will be work done in lifting this bucket is mg that both we have taken MGL plus MGL by 2. We are lifting that bucket as well as the rope. That's why mg into capital L plus MGL divided by 2. W is equal to mg if I take the MGL if I take 1 plus 1 by 2. Sorry, capital M, one is a small m. One is the capital M, other one is that small m. Clearly, we have to show the difference. Mass of that bucket is taken as capital M into GL plus mass of the rope it is taken as a small m, MGL by 2. Therefore, if you take GL common, what it will be there? M plus M by 2. GL into M plus M by 2 we will get. This is the work done in lifting a bucket of mass M by using a rope of length L. Then here L by 2 we have to take L by 2 for the rope, and for bucket no need to take. Here we are lifting the rope. That's why we'll take like this. Next, whenever we take that a body of mass M is there, a body of mass M is there in a liquid of density DL, and the density of the body is taken as dB. dB is the density of the body, DL is density of the liquid. It is, let us suppose it is the liquid. In the liquid, we have to lift a block of mass, capital M, and the density dB we have to lift. In the liquid, we have to rise or we have to lift. In the liquid of density DL, we have to lift a block of mass M whose density is dB through a height h. Let us suppose the body, a block of mass capital M and the density dB is there in the liquid of the density DL, and we have to lift it to a height h from then the work done is equal to mgh into 1 minus DL divided by dB. This is the work done in lifting it through a height h. Okay. Next, whenever we take that work done in pulling that hanging part of the chain from the table. Let us suppose it is a horizontal table. On the horizontal table, a chain of mass M is placed. Total length of this chain is taken as L, and total mass of the chain is taken as M. And out of total length, 1 by nth of its length, is only hanging from the edge of the table. Only 1 by nth of the chain only hanging from the edge of the table. Then work done in lifting this hanging part. Then the work done in lifting this hanging part to the table is. Then the work done in lifting the hanging part to the table is most important. That is MGL by 2n square. MGL divided by 2n square. Work done in lifting the hanging part to the table is MGL divided by 2n square. MGL divided by 2n square. This is the work done in lifting the hanging part. So let us suppose N1 is that initially hanging part. Then without pulling it completely to the table, without pulling it completely to the table, if I raise it to other hanging part N2. So if I want to hang it, means already N1 is that hanging part. Let us suppose one third of that, half of this half of that part, half of its length is hanging from the edge of the table. Let us suppose total length of the chain is 30 centimeters. Out of 30 centimeters, if 15 centimeters is hanging, N1 is that 15 centimeters that is hanging from the edge of the table. That I have to make it. 15 centimeters is hanging from the edge of the table. Now I have to make it to hang only 5 centimeters from the edge of the table. Then N1 is equal to 15 centimeters, N2 is equal to 5 centimeters. So the work done in this pulling from N1 to N2 is, once again, I'll repeat. Let us suppose a horizontal table is there. Let us suppose this is a horizontal table. On the horizontal table, a chain of mass capital M is placed. A chain of mass capital M is placed on the horizontal table whose length is taken as L, and mass is taken as M, and the total length of the chain is taken as L. Out of this, only 1/nth of its length is hanging from the edge of the table. Out of the total length, certain portion of the chain is hanging from the edge of the table. Then the work done in lifting it from the horizontal, lifting it onto the table. Then the work done in lifting to the horizontal, work done in pulling it to the hanging part to the table. Then the work done is to be calculated. So the work done in pulling this hanging part onto the table, W is equal to mgl divided by 2n square. Mgl divided by 2n square. This is the first one. Mgl divided by 2n square. Next. Let us suppose this is that chain. Let us suppose 1/n1 of the length is hanging from the edge of the table. That we have to make it to pull only 1/n2, only 1/n2 of its path, its length to hang from the edge of the table. So initially 1/n1 of the length is hanging. Then we have to make it for 1/n2. Work done will be in making to hang partially from the edge of the table. Work done W is equal to mgl by 2 into 1/n1 square minus 1/n2 square. 1/n1 square minus 1/n2 square. This is the work done in hanging from the hanging, or it has to make to hang partially from the edge of the table. See, total length of the chain is taken as L. Okay, first 1/nth of its length is hanging from the edge of the table. Let us suppose total length of the chain is taken as 30 centimeters. Out of 30 centimeters, first 15 centimeters, N1 is taken as 15 centimeters. 15 centimeters is hanging from the edge of the table. Then we have to make it to hang partially. That means only 5 centimeters it has to hang from the edge of the table. Only 5 centimeters it has to hang from the edge of the table. Then the work done is mgl divided by 2n square. Right? This is the work done. Next, whenever we take that kinetic energy, Ke is equal to half mv square, and potential energy Pe is equal to mgh. Energy produced by the body by virtue of its motion is called kinetic energy. Energy produced by the body by virtue of its energy produced by the body by virtue of its motion is called kinetic energy. Energy produced by the body by its position is called as the potential energy. Already we have discussed momentum. Momentum is the product of mass into velocity. Momentum is the product of mass into velocity. When we take the relation between the kinetic energy and momentum is Ke is equal to P square divided by 2m. Therefore, P square is equal to 2m into Ke. P square is equal to 2m into Ke. Otherwise, P is equal to square root of 2m into Ke. So relation between kinetic energy and momentum. Already in the previous class I have explained, if kinetic energy, if x percentage of kinetic energy increases, then percentage of increase in momentum. This is increase. Up means increase I have taken. Increase in momentum, we have to take percentage of increase in momentum. So the shortcut formula for this is percentage of increase in momentum, we have to take that as P2 divided by P1 into 100 is equal to square root of Ke is equal to P square by 2m. Then P square divided by 2m. Then Ke2 square root of Ke2 by Ke1 square root of Ke2 by Ke1 minus 1 into 100. This is the expression to calculate percentage of increase in momentum. Instead of that, if x percent of momentum that increased, x percentage of momentum is increased, then the percentage of increase in kinetic energy. Percentage of increase in kinetic energy is. Therefore, kinetic energy Ke2 by Ke1, Ke2 divided by Ke1 into 100, Ke2 divided by Ke1 into 100 is equal to Ke2 by Ke1 into 100 is equal P2 by P1, P2 divided by P1 whole square minus 1 into 100. This is the expression for the work done in. This is the work done. This is the work done increasing kinetic energy from initial kinetic energy K1 to K2 we have to increase. Then momentum that is increased P1 to P2, then what is the increase in kinetic energy that we have to calculate. This is the relation between kinetic energy and momentum. For example, it is given that the momentum of the body is increased to 100%. If momentum of the body is increased 100%, I am solving problem here. If the momentum of the body is increased 100%. 100% is increased means what? Initially some 100% is there, more 100% is increased, then percentage of increase in momentum, percentage of increase in momentum is so initial momentum is taken as cent%. If momentum body is taken as cent%, 100 will take that. So 100% extra is added. P2 is taken as 100%. P2 is taken as 100%. Therefore, P2 is doubled. P2 is doubled. Cent% is increased means initially we have taken it 100%. Again 100% is increased. So 100 plus 100, 200 will be. 100 plus 100, 200 it is. Then kinetic energy, increase in kinetic energy we write Ke2 by Ke1. Ke2 by Ke1 is equal to, what is this? P2 by P1. P2 by P1 whole square minus 1 into 100. P2 by P1 whole square minus 1 into 100. There KE2 divided by KE1. KE2 divided by KE1 is equal to. So P2 by P1. P2 is how much? 200 by 100 whole square minus 1 into 100. So kinetic energy KE2 divided by KE1 is equal to, this is 2 zeros, they'll get cancelled. Then what is there? 2 whole square means what? 4. 4 minus 1. 4 minus 1 into 100. Therefore, KE2 divided by KE1 is equal to 4 minus 1, 3. 3 into 100, 300. So if the momentum of the body is increased 100%, the kinetic energy will be increased by 300%. The kinetic energy will be increased by 300%. So let us suppose momentum, kinetic energy is increased. Let us suppose kinetic energy is increased by 21%. Quite opposite I am taking. If kinetic energy is increased, KE is increased by 21%, then the percentage of increase, in kinetic, in the momentum, then the percentage of increase in momentum is so initially kinetic energy KE is cent%. 100 we have to take that. Always we have to take like that. Earlier also P1 is taken as 100 like. So KE1 is equal to 100. Then KE2 is taken as how much it is increased? 21% extra. 100 plus 21, 121 it is. 121. Then we have to calculate percentage of increase in momentum. The formula for it is P2 by P1 into 100. Earlier also K2 by K1 into 100 we have written. There we have to write into 100 also. So P2 by P1 into 100 is equal to square root of KE2 divided by KE1 minus 1. KE2 divided by KE1 square root of KE2 by KE1 minus 1 into 100. This is the increase in momentum. P2 by P1 into 100 is equal to square root of KE2 is how much? 121. It is 121 divided by 100 minus 1 into 100. From this we'll take P2 divided by P1 into 100 is equal to square root of 121 will be equal to 11. Square root of 100 will be equal to 10. 11 by 10 minus 1 into 100. Therefore, P2 divided by P1 into 100 is equal to. So whenever we take that 10 LCM, it is 11 minus 1, 10. We'll get that. So 11 minus 1, 10. By 10 we are getting into 100. Strength and get cancelled. We are getting 100%. But I'll check that one more is there. One more problem. That is how much it is increased. For example, instead of this, if I'll check any other problem is available. If kinetic energy is increased by 125%, instead of 21%, if I take kinetic energy is increased by 121%, 125%. Okay, if the kinetic energy of the body is increased by 125%, then the percentage of increase in momentum is P2 divided by P1 into 100 is equal to square root of KE2 is KE1 is taken as a cent percent. KE1 is cent percent and KE2 is 100 plus 125. It is 225. 100 plus 25, it is a 225. So this will be 225 square root of 225 divided by 100 minus 1 into 100. So then we'll take that P2 by P1 into 100 is equal to square root of 220 by 100. That will be equal to 2.25 minus 1 into 100. 2.25 minus 1 into 100. That we have to simplify. So like this, if the kinetic energy of the body that is increased, we can calculate the percentage of increase in momentum. So next, energy, kinetic energy, potential energy is complete. Next, power. Rate of energy is called power. Power P is equal to energy divided by time or work done divided by time. Rate of energy or rate of work is called as the power. So power unit is watt. This power, it may be in the form of completely kinetic energy, completely potential energy, partly kinetic energy and partly potential energy. PE is equal to, whenever we take that potential energy, PE is equal to, PE is equal to mgh. And if we take kinetic energy, KE is equal to half mv square. So like that, we may take, let us suppose power P is equal to, half mv square. Power P is equal to half mv square divided by T. This is if energy is in the form of the kinetic energy. Our power P is equal to mgh divided by T. Power P is equal to mgh divided by P. Or power P is equal to half mv square plus mgh divided by T. Like this, we can write the power. R, power P is equal to work done divided by time. So power P is equal to force into displacement divided by time. Therefore, we'll write power P is equal to force into velocity also. Power P is equal to force into velocity. Like this also we may write. Okay, we are going to solve that numericals from this chapter. See, it is given that 300 joules of work is done. 300 joule of work is done in sliding 2 kg block. 2 kg block is there, and it is moved on an inclined plane to a height of 10 meters. Taking the value of acceleration due to gravity, G is 10 meters per second square. The work done is to be calculated. A block of mass, how much it is there? A block of mass 2 kg, that we have to lift it to a horizontal on an inclined plane. A block of mass is there that we have to lift it on the inclined plane through a height of 10 meters. The height is given as 10 meters. Then work done is to be calculated. So the work done against the gravitation, against the friction is, the work done against the friction is. Then whenever we take, this is the block which is moved on the inclined plane against the friction. This is moved on this. This is moved on this. Then mass of the block is given as, mass of the block is equal to 2 kg. It is raised to a height of 10 meters. Then acceleration due to gravity, G is 10 meter per second square. The work done is to be calculated. So the work done is nothing but mgh, as we are lifting to a height h. Work done is equal to mgh, that will calculate. Again, work done against the friction they have asked. So work done W is equal to M is equal to 2, G is equal to 10 meters per second square. H is the height through which we are lifting. H is taken as a 10. Therefore, work done W is equal to 10 tens are 100, 100 into 2, 200 joules. So work done in lifting it from the bottom to a height H. To a height H is W is equal to 200 joules. So it is given that 300 joules of work is done in sliding 2 kg block. So 300 joules of work is done in sliding 2 kg block. Actually, how much work is needed? 200 joules is needed. But whenever he has done, he has taken 300 joules of the work, then we have to take 100 joules will be wasted for the frictional force. So work done against the friction. Therefore, work done against the friction is, work done against the friction is 300 minus 200. Work done against the friction is 300 minus 200 means 100. 100 joules is needed for the frictional force. Work done against the friction is how much? It is 100 joules. Next problem is 100 joules. This is A option is correct. Next, a body of mass 5 kg is placed at the horizon and can move only on the x-axis. A force of 10 Newton is acting on it in a direction making an angle 60 degrees with the x-axis and displaces along the x-axis by 4 meters. The work done by the force is, let us suppose a body of mass 5 kg is placed at the origin of the coordinate system, that we have to move along the horizontal path, which makes mass of the body is taken as 5 kg and origin and moves along the x-axis by a force. Applied force on it, F is equal to 10 newtons, acting on it in direction by making an angle theta is equal to 60 degrees with x-axis, and displaces it along the x-axis by 4 meters. Then they ask to calculate work done by the force. So work done by the force is nothing but Fs cos theta. We need to write Fs cos theta. W is equal to F is taken as 10 newtons and S is 4 meters and cos 60. Therefore, W is equal 10 into 4 40 into cos 60 1 by 2. 2 get cancelled in 40 times. Therefore, work done W is equal to 20 joules. Work done W is equal to 20 joules we will take. Then, if it is given in the form of the vectors, then we'll see like this. If it is given in the form of the vectors, let us suppose F bar is given as 5i cap plus 3j cap newtons and R bar is given as 2i cap minus j cap meters. The work done is to be calculated. Work done W is equal to F bar dot S bar. What is the force they have mentioned? 5i cap plus 3j cap. This is distance is moved. It is displacement is taken as 2i cap minus 1j cap. Therefore, work done W is equal to 5i cap plus 3j cap, 5i cap plus 3j cap into 2i cap minus 1j cap. We have to multiply this. X means I cap. Angle between that I cap dot I cap is taken as 0 degrees. That's why we have to multiply. Angle between the I cap and J cap is equal to, I cap and J cap will be equal to 90 degrees. So we have to multiply I cap dot I cap and J cap dot J cap only. Even if you multiply with I cap and J cap, it will be 0. That's why no need to do it. First, what we have to do, angle between means force is given as 5i cap and 3j cap. Displacement is given as 2i cap minus j cap. Therefore, W is equal to 5 into 2, 10. I cap dot I cap will be equal to 1. 3 into minus 1, it will be minus 3. So therefore, work done is equal to 7 joules. Work done is equal to 7 joules. If they ask work done by the gravitational force, that will be minus 7 joules. Let us suppose we are lifting a block of mass m from the ground to a height h. From ground to the height h, work done by the lifting force is equal to, work done by the lifting force W is equal to mgh. Work done by the gravitational force, if you take work done by the gravitational force is equal to minus mgh. So if they say the work done by the gravitational force, we used to take minus 7. But have calculated, they didn't say like that. So we have calculated for positive work done. That means along the direction of the displacement, body that moves, means in the direction of the displacement. Right? This is regarding the vectors. Next, a horizontal force of 5 newtons is required to maintain a velocity of 2 meters per second for a block of 10 kg mass sliding over a rough surface. The work done by this force in 1 minute is a horizontal force of 5 newtons is required to maintain a velocity of 2 meters per second for a block of mass 10 kg mass sliding on the sliding over a rough surface. The work done by this force in 1 minute is, time period is given as 1 minute, and the force is, force applied, F is given as 5 newtons. F is given as 5 newtons, and it is moving with velocity of V is equal to 2 meters per second. Block of mass is given, mass of the block is given as 10 kg. Mass of the block is given as 10 kg, and the time period for this is 1 minute. 1 minute is nothing but 60 seconds. That will be 60 seconds. This is, so we may write this, work done is equal to what? Force into displacement. Work done W is equal to F into S. Okay, otherwise we may write this one, displacement. Velocity is equal to displacement by time. Velocity is equal to displacement by time. As they didn't give the displacement, we will write, on bringing this time period to left side, displacement is equal to velocity into time. Displacement is equal to velocity into time. Therefore, work done W is equal to F is that force, S is that displacement. In the displacement, in the place of displacement, we will write Vt. F into Vt it is, right? W is equal to, force is given as 5 newtons, and its velocity is given as 2 meters per second into time period 60 seconds. Therefore, work done is equal to 2 5s are 10, 10 into 60, it will be 600. 10 into 60, that is equal to, work done is equal to 600 joules. Work done will be equal to 600 joules. This is the work done. Next, a block of mass 1 kg is pulled on a horizontal plane of length 1 meter by a force of 8 newtons. Then it is raised vertically to a height of 2 meters. Then the work done is, a block of mass 1 kg is pulled on a horizontal plane of length 1 meter by a force of 8 newtons. Then it is raised vertically to a height of 2 meters. The work done is, then work done is equal to force into displacement. This is given, force F is given as 8 newtons. Distance S is given as 1 meter. Then work done is to be calculated. Work done raised vertically to a height of 2 meters. So initial displacement S1 is taken as 1 meter and S2 is 2 meters. S1 is 1 meter and S2 is 2 meters. Then work done in lifting it. A block of blue horizontal plane of 1 meter by force, then raise it to, okay. S1 is 1 meter and S2 is 2 meter. A box of mass 1 kg is there. It is lifted, it is pushed on that, it is pulled, pushed not, it is pulled on the horizontal table, horizontal plane 1 meter, and it is raised. And it is raised to a height of 2 meters. It is raised to a height of 2 meters. So work done in pulling it along the horizontal direction we have to calculate. Again, work done in lifting it from the ground to a height of 2 meters we have to calculate. Total work done. So total work done is equal to W1 plus W2. In moving it on the horizontal surface, W is equal to F into S plus in moving it in the upward direction, mgh we have to write. Mg instead of that we'll write F into H also we may write. F into H. So this is instead of that mgh also we may write. That will be equal to as they give. Mgh also we may write. Then W is equal to, what is the F? F is 8 newtons. S is taken as 1 meter. Plus mass is taken as 1 mass is taken as 1 kg. Acceleration due to gravity has to take it as a 10 into, it is lifted to a height of 2 meters. It is lifted to a height of 2 meters. Therefore, work done W is equal to 8 into 1, 8 plus 2 into 10, 20. Therefore, work done W is equal to 28 joules. W is equal to 28 joules. Right? Next. A 10 kg satellite completes one revolution around the Earth at a height of 100 kilometers in 108 minutes. The work done by the gravitational force of the Earth will be. Remember that work done by the centripetal force will be 0. Work done by the centripetal force is 0. And then whenever we'll take that, this satellite is orbiting around the Earth. Satellite is orbiting around the Earth. That's why it's by centripetal force. Work done by the centripetal force is 0. That's why D option is correct. Next problem. So this is work done. Force is taken as F. A position dependent force F is equal to 7 minus 2x plus 3x square newtons acts on a small object of mass 2 kg to displace it from x is equal to 0 to x is equal to 5 newtons. Then the work done is to be calculated. So work done by the variable force. Work done by the variable force W is equal to integral x1 to x2 or s1 to s2 f dx, f into dx, integral x1 to x2 f into dx. So work done W is equal to integral 0 to 5, x1 is 0, x2 is equal to 5 into f is how much? F is equal to 7 minus 2x plus 3x square into dx is there. Therefore, on applying integration. So this is integral 7x minus 2x square divided by 2 is nothing but x square plus x cube within the limits 0 to 5. What we got? W is equal to 7x minus x square, 7x minus x square plus x cube. This is we got 7x minus x square plus x cube within the limits 0 to 5. First we have to substitute the upper limit. As only the upper limit is 5, lower limit is 0. No need to substitute the lower limit. Even if you substitute, what happens? It will come 0. So W is equal to, on substituting, 7 into 5 minus 5 whole square plus 5 whole cube. Then W is equal to 7 5s are 35 minus 5 5s are 25 plus 5 whole cube means what? 125. Therefore, W is equal to 135 minus 25, 35 minus 25 will be 10. So 125 plus 30, 125 plus 10, 135 it is, 135 joules. And simplifying will get D option is correct. A particle of mass m is m and charge q is accelerated through a potential difference v volts. Its energy is. So energy is a kinetic energy. Kinetic energy is equal to charge into potential difference. Charge into PD. PD for potential difference. Therefore, kinetic energy Ke is equal to QV. V for potential. Like this, we will take. Okay. So I'm going to explain for that collisions. A strong mutual interaction between the bodies in which exchange of momenta takes place is called as the collision. So according to law of conservation of energy, according to law of conservation of energy, we will take, let us suppose a block of mass m1 is there, and it hits the other block of mass m2. At the time of collision, exchange of momenta takes place. At the time of the collision, exchange of momenta takes place. Means the force will be exchanged one another. Then after the collision, the bodies they'll move with the different velocities. After the collision, these velocities of the bodies will check it. So let m1 is the mass of the first body, m2 is the mass of the second body. This is m1 and this is the m2. At the time of collision, force experienced by the first one will be on the second one. At the time of collision, force experienced by the first one is on the second one. Therefore, first one is moving with velocity u1 bar and the second one is moving with the u2 bar. After collision, v1 bar is the velocity of the first body, v2 bar is the velocity of the second body after collision. Therefore, according to law of conservation of linear momentum, we'll take it first. Law of conservation of linear momentum. Law of conservation of linear momentum. Total momentum of system before collision is equal to total momentum of system after collision. What is that momentum? m1 u1. m1 u1 is the momentum of the first body before collision. m1 u1 plus m2 u2. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is according to law of conservation of linear momentum. According to law of conservation of kinetic energy, half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. This is according to law of conservation of linear momentum. This is according to law of conservation of linear momentum. Then whenever we take in the collision, after the collision, the velocities of the bodies we have seen. V1 is the velocity of the first body and V2 is the second body velocity after the collision. Then this collision may be elastic or inelastic. What is elastic collision? If the momentum and the kinetic energy, they remains the same before and after collisions. After the collision also, if the body consists of the same momentum and same kinetic energy, the type of collision is called as the elastic collision. In the case of the elastic collision, kinetic energy and momentum will remain constant. This is possible in the case of the fundamental particles or in the case of the gas molecules. So in the daily activities, whenever we see the collisions, these collisions are not elastic. They are called as inelastic. After collision, if After the collision, if only kinetic energy, if only momentum that remains same, but not the kinetic energy, the type of collision is called as the inelastic collision. So the velocities of the bodies after collision, V1 and V2, will see that. Velocities of the bodies after collision, they are taken as V1 and V2. V1 is the velocity of the first body after the collision, and V2 is the velocity of the second body after collision. V1 is equal to M1 minus M2. M1 minus M2 into U1 divided by M1 plus M2 divided by M1 plus M2 plus 2M2 U2 divided by 2M2 U2 divided by M1 plus M2. This is the velocity of the body after collision. So first body after the collision, and the velocity of the second body after the collision is, we'll take that M2 minus M1, M2 minus M1 into U2 divided by M1 plus M2, M1 plus M2 plus 2M1, 2M2, not M1, 2M2 U2 divided by M1 plus M2. This is the velocity of the second body after the collision. If initially first body is at rest, if initially second body is at rest, if initially second body is at rest, second body velocity will be 0. If the second body velocity will be 0, means it will be 0 and it will be, oh, no. For both of them it won't come. If it is V1 is equal to M1, V1 is equal to M1 minus M2 into U1 by M1 plus M2. Then plus 2M2 U2 divided by M1 plus M2. If initially second body is at rest, this is a 0. This is 0 as U2 is equal to 0. Then second body whenever we take, already we have written M2. This we have to write it is M1 U1. This is taken as M1 2M1 U1. M2 minus M1 into U2 divided by M1 plus M2 plus 2M1 U1 divided by M1 plus M2. So initially, if the second body is at rest, U2 will be 0. Therefore, the velocities of the bodies after collision, the velocities of the bodies, V1 is equal to M1 minus M2. V1 is equal to M1 minus M2 into U1. And V2 is equal to 2M1 U1 divided by M1 plus M2. See, V1 is equal to M1 minus M2 into U1. V2 is equal to 2M1 U1 divided by M1 plus M2. This is the, these are the velocities of the bodies. See here, in this case, they'll ask if the mass of the second body is much greater than, mass of the second body is much greater than that of the first body. In such case, mass of the second body is much greater than the first body, means velocity V1 is equal to minus U1 we will get. Then velocity of that second body is much greater than the velocity of the first body, then V2 is equal to 0. Second one, if the mass of the first body is much greater than that of mass of the second body, mass of the first body is much greater than that of mass of the second body, then V1 is equal to U1 and V2 is equal to 2U1. This we are to remember. Right. So whenever a sphere that falls from height h and rebounds to the height h1, let us suppose a sphere that falls from a height h1 and rebounds to a height h2. After the first rebounds, it rises to a height h2, and after the second rebounds, it rises to a height h1 h2, like it falls from a height h1 h and falls on the ground, and afterwards it rises to a height, and afterwards it rises to a height h1. Let us suppose a sphere that falls from a height h from a height h. Then it rises to the height h1 for after first rebounding. After first rebounding, it rises to a height h1, and after second rebounds, it rises to a height h2, and the third rebounds, after third rebounds, it is h3. Like if I take nth rebounds, for nth rebounds, we have to take height raised. So this is the first, it falls from height h and rises to a height h1, again falls down, again rises to that height h2, falls down, again rises to the height h3 and falls down. So at the final, it attains that height hn. Hn is to be then height attained by that freely falling sphere on a floor after n rebounds is hn is equal to e power 2n. Hn is equal to e power 2n into h. So this is the important formula. Hn is equal to e power 2n into h. Then velocity of the sphere after n rebounds, E is equal to velocity of the sphere after n rebounds, Vn is equal to e power n into h. E power n into h. Let us suppose this is that total distance covered by the sphere after n rebounds. So d is equal to h into 1 plus e square divided by 1 minus e square. Then total time taken for n rebounds. If t is the total time taken for n rebounds, so then t is equal to 2h divided by g into 1 plus e divided by 1 minus e. 1 plus e divided by 1 minus e. This is that total time taken for the sphere for n rebounds. Okay, I'm going to stop the class here, and I'll share you the synopsis and formulas tomorrow.